I hate you, I love you, hate that I love you, don't want to, but I can't put nobody else above you.
Hello friends, welcome to my YouTube channel. So here in this video we will see the tutorial for shell and tube heat exchanger. So how to prepare this shell and tube heat exchanger in PVA Lite software. So before going to that, we will see the small introduction about the shell and tube heat exchanger. So the image you are seeing, this is what our shell and tube heat exchanger. So the name shell, it is there, and then tube inside there are a lot of tubes are there. We call it as a tube bundle. And so here you see the flow of direction. So here you see the fluid in from this portion, so it enters through these tubes, then it comes out from these tubes, so it will go out like this. So then in the shell side we will enter this media. So here it will enter, and they have provided some baffles in this, so it will go like this and then went outside like this. So there are two inputs and two outputs. So this is the arrangement of this shell and tube heat exchanger. So we'll go to PV Lite and prepare this shell and tube heat exchanger. So we'll click this dish end first. So we'll rotate this and choose this elliptical type dish end, and we can choose the diameter for this dish. It is 1000. Okay, and then we can enter the SF50. So if you want, you can change the diameter 1500. Okay, and then so thickness we need 8 mm. Okay, then the nominal thickness, internal corrosion allowance we can keep 3 mm. Then the pressure, it is we can enter 1.5 bar, so 1500 pascal, and the temperature 100 degrees Celsius. So external pressure will be in atmospheric, and then external temperature we can give 60. Okay, so now in this case you see the pressure is increased, so the thickness we need 12 mm. Okay, so if you want you can cross check this. First we can save this model, shell and tube heat exchanger. So HS is the short form of heat exchanger. So you see the metal design temperature, it is higher than the required. So you see this computed, it is 23 and we gave 29 around. We can enter that. Here it is that we can give 20. Okay, now save this. Now we can check this analysis. See, there is no error. So then we can create a cylinder here. So the cylinder length we need to provide. So it can be 1000. Okay, so then you see everything remains same as the constraints we gave for distance. So then for this we need to give the description. So you can enter this left side distance. Okay, and this also left side channel shell. Okay, so then we can enter this left hand side channel flange. So you can select this bolted flange, and here you see the flange length we need to change. So you can give 150. And here you see perform a flange calculation. In this we can select this type of flange, this type of flange, and you can choose this standard type of flange. We enter this ID 1500, so that 60 inches will be there. NC series A we choose, and then include corrosion and flange thickness. So the hub diameters will be automatically calculated. Now click update dimension. So here you see all the dimensions has been automatically calculated, and here you see everything is this okay and okay, everything it is passed. So we choose this gasket type. So you can spiral wound gasket. Okay, spiral wound gasket we can choose. Select this. Now search for design. So this is what the quick calculation about this design. Okay, now click OK. So see the channel flange has been created like this. Then we'll create this tubes. So in tubes we need to select this tube analysis method. It is TMO or ASME. Okay. Exchanger type. It is a tube type heat exchanger. Then tube properties. We can give. Yes, we can choose this fixed type. Here there is a no joint. Then we'll go for tube properties. In description we can write tube shell and tube heat exchanger, or tube for heat exchanger. And then here you see the distance from node. Okay. And then the tube type. So we can choose this as flange, extended as flange. Okay. Then outside diameter. Okay. Tube extended as flange. Pick this button, and then tube sheet thickness. We have to enter this. So later, and then coming to tube data. So here we can choose number of holes can be 325, triangular pitch, and then the wall thickness we can enter 3 mm, corrosion allowance 0, and then the outer diameter of the tube will be 25.4. Then the pitch we can enter so here we can enter 19, and the pitch will be 25. Okay. And then the length of the tube portion, it will be 30. Then the radius of outermost tube full center we can enter 150. And then distance between innermost tube center, so here we can give 30. And straight tube length we can give 1600. Okay. And then this straight tube length measured between outer faces. Okay, from outer to outer. Then tube layout assistant can check this. So this is how it will be. So see. So then everything we have entered, and then here you see the tube joint type. There are many types are there. We choose I type. Here there is seal and no weld. Okay. Then coming to this tube sheet, GT tested. No. Then weld leg size, if any, we can provide two. mm, Okay. Here you see TMOS standard tube sheet input. Maximum distance from tube sheet to first tube support, it is 500. And then here also you can give maximum distance between two second tube support, it is 300. Then everything we have filled in this data. Then we'll go to expansion joint. So in expansion joint, there is no expansion joint. Okay. Now click this load cases. So here I can enter this pressure. So pressure it will be in kilopascal. So we can enter the same as what we have entered for this previously. So 1500. And then so this is what the design pressure. And then the maximum allowable, maximum operating pressure, it is let it be. And then the design temperature. So here you see for shell it would be 100. And then so everything we have filled in this. Then mean metal temperature along length, we can give if you want to change the material, you can change it here for tubes and tube sheet. So then so tube required thickness, it is 0.18. Okay. Now almost we have filled everything in this tube. So we can enter this tube sheet. Then we can select the material for this. See, a lot of materials are there. And then I'll go and check this design code. So here you see the MDMT, it can be 20 for both. Okay. And then coming to this load case description, can enter design or load. Okay. Now click OK. So see the tube. So here you see outermost tube hole center. You can increase this 1500. Click OK. Enter 1000. And the number of holes we can enter 600. Straight tube length, it is 1600. So it is from outer to outer. And then here you can reduce this little, 750. Okay. 500. Okay. So can I enter this increase this number 1000, 3000. So see this is what our tube. So you can cross check this flange. So here I can click this flange. The flange OD it is 1675. So here you see 1855, and in this tube sheet, so the OD we can enter 1865. Okay, and then the tube sheet thickness we need to change. So tube sheet thickness we need to enter 50. Click OK. See, our tube has been generated. Then we can increase this distance. So straight tube length it is we can give 3000. Click OK. So see, this is how it will be. And again, you can create a shell here and enter this cylinder length and choose 1500 and 2500, 2750 or 2800, 3000. So it will be an very less value. So okay, we can choose this tube sheet. So we enter this 3000. So we'll change that 3100. Now you see it has been matched with this. Here again we need to create a bolted flange in opposite direction. And here we need to increase this thickness 150, and the data will be similar to this. So here you can check. So we entered 60 nominal size and then grade 1.1, and then 52 bolts holes are there. And then you can go and check this. Here you can perform this. It is 60 and obtain this A series. Okay. And then the gasket we entered a spiral wound gasket. Okay. So then I can click OK. See both the flange we have created like this. So then we need to create a cylinder here. So for 1000 mm. Okay. Then we need to create a addition. It's an elliptical type addition. Okay. So we have drawn this outer model of heat exchanger. So then here we need to give this saddle support for this too. So we can select this, and here there is an option for saddle. So we can choose the distance from thumb node. It is 40 here. So from 40 to here we can enter 250, and the saddle dimensions will be like this. As it is. So we perform a saddle check and then perform anchor calculation. Saddle bolted to steel foundation. Okay, and click OK. See here it is created like this. If you want to change any dimensions, you can change it here, so like width or length, and then thickness. So everything we can change. And then if you want to move little, you can move it here 300. And then so wear plate and shell materials are same. Okay, if it is same, you can press click OK here. Number of bolts it is 8. We enter bolt intention. Okay, and then the thread types PMO. Bolt nominal diameter we choose 32. Okay, So similarly, we'll have to create one more saddle here. Again, click this, add a new saddle, same as first. And the distance we need to enter. So here we entered 2500. Let me check this. Okay, came exactly. So then we need to create a nozzle for this heat exchanger. So here you can select this shell, and there is option for nozzle input. So this is with reinforcement pad. So this one it is without reinforcement pad. So we'll keep this enforcement pad for this because we are entering more than 50 NB nozzle. So you can and rename this nozzle number, and you can put this nozzle material, and then the schedule it is 40, and size of this will be 80 NB. Okay. Then here you can press the actual thickness. You can enter 6 mm. So UG failed it is showing. Enter 6. So if you want to perform any nozzle calibration, you can perform this here. Maximum allowable working pressure. Okay. Then the weld strength it is okay for this. So here we can choose this flange glass and what you call the grade, and then distance from this. Okay, from node it is 0. Can enter 500. Now if you want to change the material, you can change it here. Here you can enter 12. There is no area calculation. This is a small opening. Okay, you can enter 10 and check. Click OK. So see, this is how it is created. So you can change this 100 MB. Okay. So this nozzle we want it in downward direction, like how we so this nozzle it should come in this top and bottom side. So let me choose this. So we can increase this size. We can enter 200. Click OK. And here you need to change the direction of this. It is 90 degree. Here you see there are some UG failure. So we can increase this thickness. So 12. Okay, it is passed. Now click OK. See the flange it is creative, and if you want to increase the projection, you can increase this here. So similarly, add a new nozzle. So the everything remains same in this distance from node it is 500, and the layout angle it is 270. Okay, now click OK. So now we can rotate and see both the flanges has been created in this. Then what else? Here also we need to create one flange, and here one flange. So again select the shell, and then make a nozzle. So here we can enter 200, and then actual it is 12 mm, or so distance from node it is 150 or 250. Then the layout angle it is 90, and the projection 200. So you can choose this. Now click OK. See the nozzle projected like this. So if you want to move little, you can move it here. Enter 500. Okay. So again, we need to add a nozzle, add a new nozzle. Here in this case, 270 degree. Distance from node, it will be 1500. Everything remains same. Now click OK. So still we need to move this 2000. In front view you can check. So this one move it little. If you want to increase this length, you can increase. So the tube length 4160. Okay. Here also 4000. Okay. And this saddle also we can increase 3700. This nozzle we enter 3000. So see our Allen tube heat exchanger. So this is how it will be look like. And, can create later. Now analyze this. See there are no error in this report. Can generate PDF file. So see this. This is how. This is what our input data. So 1500 kilopascal of design, shell and channel side, 100 degrees Celsius RT. So all our design report, everything is okay. Vessel design summary you can check. So shell and then head, the material class, so the thickness, tube height and flange bolting. So it is an ellipsoidal dish and then a cylinder, body flange, cylinder, everything remains okay. And then the saddle, wasted plan view. Okay. So thanks for watching this video. If you like this video, please give comment, like, share. Also, please subscribe my YouTube channel. So thanks for watching.